So let's continue our discussion of inductive definitions. So recall that functions like factorial and insertion sort have natural inductive definitions in terms of smaller subproblems. And the attraction of looking at inductive definitions is that we can very easily come up with recursive programs that implement them in a very obvious way. But the challenge is in identifying the subproblems and making sure that they are not overlapping. So in the case of factorial, remember that any smaller input to factorial will be a subproblem. Similarly, for sorting, you can think of any segment of the list to be sorted as a subproblem. And in general, we are looking at recursive solutions or inductive solutions where the solution to the function f we are trying to define is derived by combining solutions to the subproblems of this original problem. And so we compute f on smaller inputs than y. So let's see how this works with a very familiar series that you may know of called the Fibonacci numbers. Okay? So let's define the Fibonacci numbers as follows. The first two Fibonacci numbers are 0 and 1. And then every successive Fibonacci number is obtained by adding these two. Now it is instructive to see, even before we begin, how we would enumerate the Fibonacci numbers. So we know that the first two are 0 and 1. Okay? And then you know the next one is the sum of these two, so the next one will be 1 again. Next one will be 2, because it's 1 plus 1. Next one will be 3. Next one will be 5. Next one will be 8. Next one will be 13, and so on. Right? So it's very clear that though these numbers have an inductive definition, right, and there is an obvious recursive function that goes with it, which I'll just mention in a minute, there is a very efficient way of enumerating these numbers directly, almost in linear time. So how does the definition of the function go? Fibonacci of n just says if n is 0, return 0, if n is 1, return 1. So if n is 0 or 1, the value is n itself. Otherwise, you compute value recursively using this criterion, Fibonacci of n minus 1 plus Fibonacci of n minus 2. And finally, whatever value you have computed, you return. So where is the catch? So let's see how this would work on a small input like we just saw, Fibonacci. So we just saw that Fibonacci of 5 is 5, right? We know that we start with 0, 1, 1. So these are the arguments, right? So the values are 0, 1, 1, 2, 3, and then 5, right? So we are trying to compute this fifth Fibonacci number, which we computed very fast. Okay, but let's see how this recursive thing would actually work. So if I call Fibonacci of 5, recursively it would ask me to compute Fibonacci of 4 and 3. Fibonacci of 4 in turn will ask me to compute 3 and 2. Now 3 in turn will ask me to compute 2 and 1. Then 2 in turn will ask me to compute 1 and 0. Now fortunately for 1 and for 0, I have a base case, so I will get those values 1 and 0 respectively. So since I've got 1 and 0, I'll now be able to compute Fibonacci of 2 as a sum of those, and I will get the answer 1. Now when I turn to Fibonacci 1, again it's a base case, so I get the answer 1. So now I have both the answers required for Fibonacci of 3, so I get the answer 2. Now I go back and I compute Fibonacci of 2, but remember I've already computed it, but because I didn't make note of this, in some sense I'm blindly doing recursion. Fibonacci of 2 will again ask me to compute Fibonacci of 1 and 0, which will again produce the base case as 1 and 0. So I will again compute Fibonacci of 2 as 1. And now with both Fibonacci of 3 and 2 available, I will get the answer of Fibonacci 4 as 3. And now I will go back and compute Fibonacci 3 yet again. Right? So I will do this whole tree again. 3 calls 2 and 1, 2 calls 1 and 0. These return the base case. That gives me a value for 2. 1 returns the base case. This gives me a value for 3. And finally, after all this, I get the value Fibonacci of 5. Right? So the problem we can see is that functions like Fibonacci of 3 have been computed twice in full complexity. Other functions like Fibonacci of 2 have been computed 1, 2, 3 times, and so on. Right? And of course, Fibonacci of 1, though it's a base case, has been called several times 1, 2, 3, 4, 5 times. And Fibonacci of 0 has been called 3 times. Right? So this is the big problem with this recursive computation, that we seem to be computing too many things. See, ideally, in order to compute Fibonacci of 5, I know I need 4, 3, 2, 1 and 0. Right? So I need only 6 values totally to be computed, and I'm making a lot more than 6 computations in this. So the crux of the problem is that there are these sub-problems which arise in different contexts within this recursive computation. So Fibonacci of 3 is generated both by the original call to Fibonacci of 4 and the nested recursive call to Fibonacci of, so the original call to Fibonacci of 5, sorry, and the nested recursive call to Fibonacci of 4, right? So we have this entire tree of computation which is duplicated. And because of this kind of wasteful recomputation, overall the computation tree grows exponentially. Right? So you'll actually find in general that in order to compute the nth Fibonacci number, you actually do some exponential in n steps. Even though we can see that you can just compute the nth Fibonacci number in linear time. We just saw it, right? You just compute it as 0, 1, 2, 3, 4 and so on. So one way to get around this is to make sure that you never re-evaluate a subproblem. Okay? So you build up a table, which is sometimes called a memory table. And what does this table do? It just keeps track of every value for which you have computed the function before. Okay? So it's just a lookup. In a language like Java, it could be a hash map, or a language like Python, it could be a dictionary. Every time you call f on a value x, you just store x comma fx in this table so that you can look it up and see if you've already computed it before. Right? So it's called memoization. Okay? So this term memoization comes from the word memo, which some of you may have heard. So a memo is a note, okay, which reminds you of something or reminds somebody else of something. So a memoization or a memo table or a memory table is supposed to remind you that the value you're trying to compute has already been computed. Okay, so how does memoization work? So we have this memo table here, right? So this is our memo table. So in this memo table, okay, it's just a table where we'll keep different value of k and fib k as we compute them. Right? We assume that we have computed nothing. We don't even know the base case. We are just going to apply the recursive definition, but every time we compute something, okay, we will first look up the table before we compute it recursively. And if we have to compute it recursively, then we will store each newly computed value back in the table. Right? So let's start as before. We wanted to start by computing Fibonacci of 5. So the recursive definition says that we should call Fibonacci of 4 and 3. Now we go to 4, we are just doing this recursion left to right. So 4 will call 3 and 2. 3 will call 2 and 1. 2 will call 1 and 0. At this point, we try to evaluate Fibonacci of 1 for the first time. When we evaluate Fibonacci of 1 for the first time, we hit a base case and it tells us that this value is 1. So we will return this value, but we will also store it in the table. Right? So now we have made our first entry in the table. It says Fibonacci of 1 is 1. Then we look at Fibonacci of 0. And again, it's a new value. We get it from the base case, but we have never computed it before. So now we have computed it by computing the base case. And again, we put an entry in the table saying Fibonacci of 0 is 0. So with this, as before, we have got Fibonacci of 2. So up to this point, we have not saved anything, except that we have also now, because we have computed Fibonacci of 2, we have added to this. Every time we get a new value computed, we put it in the table. Now to continue with Fibonacci of 3, I need to go back to Fibonacci of 1. Of course, it is a base case, but what my table thing tells you is that you should look at the table first. Right? So we go down the table. Hopefully, it's organized in some efficient way, but in the worst case, let's just do naively scan it. We look, have I ever done Fibonacci of 1 before? And it says, aha, I have done Fibonacci of 1 before. So it will look up that value without calling the base case, without looking at the function definition, and just return Fibonacci of 1 is 1. So we have indicated by turning it orange that this call was actually returned from the table. It didn't actually require a computation. So now that I have 1 and 1, Fibonacci of 3 is now 2. So now I have to continue with Fibonacci of 4. So I now have to call Fibonacci of 2 again. So now it will go down and say, have I ever seen Fibonacci of 2? And it will say, aha, I have. And therefore, without doing the recomputation, it will look up this memo table, and again we mark it as an orange value because it came from the table. It returns the value 1 which we stored in the table. So now having computed this, we've got Fibonacci of 4. So we compute Fibonacci of 4 to be 3 from the recursive definition. And then again we store it in the table. So every new value that we compute, we store in the table. Whether we are going to use it again or not, we don't know. But if we want to use it again, it's good to have it there. Right? So we just blindly put everything that we ever compute back into the table for future use. Now we come back to the top. The Fibonacci of 5, we have got the left branch. We need the right branch. We go to Fibonacci of 3. Earlier we had blindly reproduced this entire tree at the bottom in order to get Fibonacci of 3, but this time we are smarter. We go down the table and we find that 3 has been computed before and the value is 2. So we get this value of 2. And now we have both the answers that we need for Fibonacci of 5. And so we get Fibonacci of 5 is 5. And again we put it in the table, although in this particular case we are not going to use it because the computation is over, but it could be part of a bigger computation. So we just keep doing this. So what you can see in this is that the computation tree, which used to be exponential, is now linear. Now why is it linear? Because every value which is in blue occurs only once. Okay, and every value which is not in blue is a lookup in the table, so it costs nothing. Okay? So therefore, we have now made, so this more or less this memoized Fibonacci is what we do, although we do it in a different order when we actually compute it by hand. So just to see what the memoized Fibonacci looks like. So the green code is what we wrote earlier. Fib of n, if n is 0 or 1, set the value to n, else set the value to fib of n minus 1, fib of n minus 2 and return. So now we will introduce the memo bits, which are the red ones. So we have a table which we will call fib table, whose values are indexed by the position. Right? So fib of 6, if I compute, it will go into fib table 6. So when I get an argument to fib, the first thing I do is I look whether fib table has an entry for that. So if fib table of n exists, return whatever it says. Okay. If it doesn't exist, then we compute it. Now if it, once we have computed it, before we do anything, we put it back in the table, so that next time we will not compute it again, right? So every new value is put back in the table and then we return it. So when we return a value here, it has been computed for the first time, but it has been stored in the table. So the next time I get the same n, I will come here and I will exit at this point. Okay? So this is our memoized Fibonacci. It just has a very simple check for the table at the beginning, and when you compute the value, it puts it back. So this is a very simple thing that you can do. You can do this for any function. So supposing you had some recursive function or inductive function with 3 arguments, then you would just have a table with 3 indices. So let us call it f table. So computing f. So you have some inductive way of computing the value from the subproblems. So first you look up, have I ever seen this x, y, z before? If so, just return it. Otherwise, compute a new value for this given x, y and z in terms of the recursive definition from the inductive structure of the problem. Having computed it, put it back in the table. Okay? So that you never have to compute it explicitly again. And then you return. Right? So this is a generic scheme which can be applied to any recursive function that you might write. The only thing you have to do is you have to make sure that you can design a table with the appropriate lookup and look it up efficiently, because if you spend a long time looking up the value in the table, then that's lost. So if you can make it a kind of array lookup, that's ideal. So this is memoization. So the other term that we introduced in the last lecture is dynamic programming. So what dynamic programming does is it tries to eliminate the recursive part of evaluating an inductive definition. So in memoization, what we do is we evaluate the inductive definition recursively exactly as we would normally. The only thing is we keep a table which helps us to avoid having to compute the same thing twice. In dynamic programming, you anticipate what the table should look like and how the values in the table depend on each other. Okay? So supposing we are computing Fibonacci of 5, then by some simple analysis of Fibonacci, we know that if Fibonacci of 5 requires anything at all, it requires things smaller than it. And the smallest thing you can get is Fibonacci of 0. Therefore, from Fibonacci of 5, we immediately know that the subproblems that could be of interest to us are all subproblems between Fibonacci of 0 and Fibonacci of 5. Okay, Fibonacci of 5 is not going to require Fibonacci of 6, 7, 8, nor can we call Fibonacci with a negative number because it's not defined. So there's a very small and finite set of values which we need to consider. Now the next observation is that we can compute the dependencies from the problem structure. This is from the inductive definition. So Fibonacci of 4 is equal to Fibonacci of n is n minus 1 plus n minus 2. So 5 depends on 4 and 3. So I would say that there is In order to compute 5, I must have first computed 4 and 3. So I will draw an arrow from what it depends on to what it is. So 5 depends on 4, 5 depends on 3. So I put an arrow from 4 to 3 and 4 to 5 and 3 to 5, saying that there is this dependency. In turn, 4 depends on 3 and 2, and 3 depends on 2 and 1, and 2 depends on 1 and 0. And of course 1 and 0 are the base cases, and they don't depend on anything, right? So the dependencies will form a DAG. Why do they form a DAG? Well, it's quite obvious they must form a DAG, because if there are cyclic dependencies, you can't compute one before the other, right? So it's a very natural thing in any kind of dependencies, whether it is dependencies between tasks, as we saw when we did DAGs to begin with. There are many, I have to do something before I do something else. This is precisely that. Right? It's saying that if I cannot compute Fibonacci of 2, I cannot compute Fibonacci of 3, because it has to be done first. Now that I know these dependencies, right, I can now enumerate them in any topological order, such that when I reach a value to be computed, everything it depends on is known before. Right? So for example, here a natural order would just be, of course, 0, 1, 2, 3, 4, 5, because both of these are now elements with no incoming edges. So I can either start my topological order with 0 or with 1. Okay? So let's assume I start with 0. So I know that Fibonacci of 0 depends on nothing. It must be a base case, so I fill it in. Likewise, I know that Fibonacci of 1 depends on nothing, so it's a base case, so I fill that in. Okay, so at this point I've done both of these. Now since I've done both of these edges have gone, so there's nothing pointing into 2. Right? So this is just topological sort. The basic topological set is also gone. So 3 still has a dependency, namely 2, but 2 has no dependencies anymore, because both 1 and 0 are available. So I can fill Fibonacci of 2, then fill in Fibonacci of 3, 4 and 5. And this is exactly what we did earlier when we tried to compute Fibonacci by hand. Right? So what we were actually executing when we were writing off the Fibonacci numbers left to right by just looking at the previous 2 and computing the next one is actually what is called dynamic programming. So dynamic programming for the Fibonacci function just consists of iteratively filling up the table. You start with the value 0 and 1, and then for 2 to n, and of course if I is if n is less than this, we will not go through this iteration at all. For 2 to n, we fill up the ith entry from the I minus 1th entry, the I minus 2th entry, but then as we saw before, these two values occurred earlier, so they were already filled. Okay? So I have converted my memo table filling from a recursive computation, filling on demand as it were, to filling blindly from beginning to end, which is dynamic programming. So to summarize, we have seen two strategies to make recursive computations of inductive functions more efficient. The first is memoization. So what memoization does is whenever it computes the value of the function in a subproblem, it puts it into a table. And before it calls the function recursively to compute a value, it will look up the table to see if this value has already been computed. So the same value is never, the same computation never happens twice. In dynamic programming, on the other hand, we analyze the problem structure to identify the subproblems. And we know that this subproblem structure satisfies a DAG. Okay, the dependencies must form a DAG, because if it's not a DAG, then we'll have cycles and things will not be able to solve anyway. And having done this, what we get from dynamic programming is iterative evaluation. Okay? So this is actually in practice a big saving, because in most programming languages there is a hidden cost to recursion, because every function call actually requires a certain amount of operating system and programming language bureaucracy, some administrative work to declare some memory on the stack and so on. And this is avoided completely in a dynamic programming solution. Right? So it is a big saving to be able to remove, even though memoization is going to give us an optimum number of recursive calls required for a given problem. It's not going to call anything twice. Okay? It will still involve recursive calls. And recursive calls can be expensive in their own right. For the sake of algorithms, we typically treat function calls as kind of unit cost operations, but in practice it's not the case. So dynamic programming can be a huge saving, because it actually converts an optimized recursive thing into an iterative scheme.